All right, I'm RIK ARENDS. Welcome to my talk. As I said, or as Edward said, I found the language to use, which is Rust, after a long journey. And as is sort of commonly known, Rust is a slowly compiling language, but I choose to refute that. So every single demo and every single thing you see in this talk, I'm going to compile on stage. So I'm going to start with compiling my slides. I'm going to do a cargo clean, as you see. And then I'm going to compile Makepad Studio, which is our work-in-progress IDE. Everything I'm showing here is a tech preview. You can play with it, you can download it, but it is a tech preview. Let's see, I'll make the text a little bigger. So I'm going to start by programming my slides. This is very difficult now that I only have one hand. Hello, GOSIM. So, well, the slides are now running in our IDE, but I'm going to run the slides full screen. So let's run the slide application as a separate application. Here we go. Maximize it. Yeah, live application building with Makepad. This was a little bit of live application building. I was live coding the slides application. And I want to talk a little bit about what we lost as developers. If you're young, you might not remember or ever have seen it, but in around 2000, in the late 90s, we had Visual Basic, we had Delphi, we had tools that allowed us to design applications and run applications with a very short iteration cycle. And then the platforms fractured, we got web, and we kind of lost that way of application development. And Makepad is about trying to get that way back. In a modern way, of course. We don't live in the 90s anymore, so you don't drag and drop Windows applications together. But we're trying to bring a new design front end to that. So a long time ago, I founded a cloud IDE company called Cloud9. We built a code editor called ACE, which you might have seen in GitHub at the time. It was the editor in GitHub. Code Academy, or Khan Academy used it as well. It's been everywhere. But we wrote it in HTML. We wrote the entire UI of the IDE in HTML. And that is actually still being done. Visual Studio Code, the most popular developer tool at this point in time, is written entirely in HTML. However, when I was doing this, and I still think this is the case, HTML was a very complicated way of defining user interfaces, especially if the user interfaces had a relatively large amount of data, such as a code editor, which is, for computers, it's actually not a large amount of data, but for browsers it is. For HTML it is. And yeah, you know, you build a web-based IDE, you build it in HTML, but we were struggling to just be able to do what Visual Studio did, or just be able to do what Eclipse or IntelliJ did. We couldn't really innovate it because there was just no space in the rendering time. It's just too slow. So I couldn't innovate it. What I wanted, for instance, was very basic. I wanted to animate a code fold. That's what I wanted to do. But with CSS at the time, it was just too slow. I couldn't do it. So innovation was stalled. And also, it was very hard to control. So once you had it working in Chrome, it would break in Safari or Firefox, or, you know, it was a really very frustrating experience to build what I thought was actually very simple. A code editor isn't a hard problem per se. It's not a hard problem. It's not an insane amount of data. It's just, it's just really bad to do in HTML and JavaScript. So after that startup, I decided to start over completely. In this case, I didn't throw away JavaScript yet. I was like, okay, JavaScript I can do. You know, this is quite a fast language. It's been optimized with V8, but HTML is bad. So what if we do it in WebGL? What if we build the whole UI in WebGL? And WebGL is a GPU API that allows you to write shaders. Those are little programs written in GLSL, that's the language, that run on the GPU. And you should imagine this as a little computer program that runs for every pixel on the screen. You can also run it for the geometry, but it runs for every pixel. And that sounds ideal for styling, right? So I tried and tried and tried again to do this in JavaScript, and every single time I ran into performance problems with the garbage collector, or Chrome would crash after a while. And I want to quickly show you the final result of my JavaScript endeavors. Yeah, I have to. My IDE has a built-in web server, so I'm abusing my IDE web server now to serve my old IDE in JavaScript. So here it is. It's a bit tiny. Let's make it a bit bigger. I mean, at least I did that. I added support for scaling that the browser does. This is all WebGL, so none of this is automatic. Everything you have to do yourself. So this was my JavaScript IDE. And it had a whole bunch of cool features, right? Like this was the code editor, and this was an AST editor for JavaScript. So this is the formatting of an array switching mode. You know, there's no intermediate stage here. You cannot break this structure in the editor because it will just not allow it. But it still had live coding, so I could do, let's see if I can, oh yeah, you can just live code everything, because JavaScript is an interpreted language. I can hot load the code. And another thing that I figured out was how to write shaders in the host language. So since shaders are written in GLSL, which is a form of C, that was not a nice match for JavaScript. So what I did was I took JavaScript, parsed it, added some shader semantics, and then essentially ran a simplified version of JavaScript on the GPU. Whilst making it very easy to pass data from the CPU to the GPU. And this is the idea that stuck. This is because I could do this UI. It worked very well. The only problem was my benchmark for if something is good is if I can use it myself, right? And what am I doing? I'm building an IDE. So if I can't use my IDE to build my IDE, it's a crap one, right? It's not good enough. And this one was not capable of doing that. I tried to make it do that, but Chrome would crash after 30 minutes of live coding, right? So, and there was no way I could solve that reasonably, because I already tried to submit bugs to Chrome. I think I still have a bug in Chrome that I occasionally get updates from 10 years ago that has never been fixed. So I gave up on the web platform in the sense that it's a thing that I could improve. It's just a thing that I have to live with. And if I have to live with something that doesn't work, then I should change my job. So let's get back to the slides. Where's my slides? All right. I'll show you this UI in a second, what it does and what it means. That one. I want it full screen. So, so the good part of the JavaScript IDE was that you could do real live coding, right? You can hot load a piece of code in a JavaScript engine because it's designed to do that. What apparently it isn't designed to do that is if you do that for 30 minutes, because yeah, that was very crashy. But the bad parts of JavaScript, besides being crashy, was also that the garbage collector was in the way. So when you're trying to get smooth frame rates, when you're scrolling or when you're editing or when you're working on a UI, and you have a garbage collector, you get random hiccups. So, and these random hiccups are incredibly difficult to fix, if at all, because you have no control. A garbage collector is essentially this thing that runs in the background that cleans up your mess, and you have no control when it runs, and you have no observable ability of what it does when. You just have to sort of believe it, and that makes it impossible essentially to guarantee frame rates, right? Which is Maybe not a problem for an IDE, but if you want a smooth scrolling mobile app or something like that, you're not going to be happy with all the hiccups of a garbage collector. So now what, right? I spent 5 years of my life, from 2013 to 2018, to do this in JavaScript. I learned JavaScript upside down. This language I could parse. I've written parsers for it. I've done all sorts of stuff. Yeah, now what? I kind of felt really sad because I wanted this live coding IDE. This is what I wanted. I wanted Visual Basic. I wanted, well, not Visual Basic per se. I wanted a really fast Visual Basic, but I couldn't get it. And this is when my co-founder of Makepad, currently Eddie, who was working at Mozilla at the time, introduced me to Rust. It's like, hey, here's this new language that has all these features, all these facilities of a modern language, right? It has all the niceties that you expect from a modern language, but it's extremely performant, right? It's extremely fast. It doesn't have a garbage collector. It uses something called a borrow checker, which is a form of compile time memory management. I'm not going to go deeply into that, but suffice it to say that it gives you the performance of C++ without the memory issues, including manual management and buffer overflow. So it's safe and it automates most of it, as long as you can live with the borrow checker. So yeah, we started over with the same idea, build a live coding IDE. Rust is compiled and it uses LLVM as its backend. LLVM is means low-level VM, and it's a modular compiler architecture. So it originated at Apple because I think they needed it for their bridging of architectures to be able to jump from different CPU architectures without having to change the front-end language. The idea is that you have back-end modules, and you have front-end modules, and you have optimizers. The back-end modules are designed to compile intermediate code to the different CPU architectures, whereas the front ends are languages. So you have Clang, which is for C and C++, and Rust sits actually next to Clang in the LLVM architecture. So it's a different front end for the same compiler architecture. This is also why Rust could mature and grow so fast, is because they essentially inherited the compiler optimizations and compiler optimization modules and code generator engines that were built for Clang and for Swift. They share the same module. So that is extremely powerful, because we now get decades of compiler optimizations in Rust. Even though Rust is new, the compiler systems are much older. Rust is a typed language, so that means that yeah, it's very strictly typed. Yeah, how to explain this to a JavaScript developer is always a bit mind-bending, but it also caused me, I thought C++ was a typed language. It's not really very typed. It's very weakly typed in that sense. You very easily pass around numbers, whereas in Rust you are encouraged to give these numbers a type. So instead of saying temperature is a float, you give temperature a type of temperature. And if you then can define the mathematical operations that you can do with it, you can restrict the amount of bugs you can do. So for instance, if you have typed temperature and, I don't know, volume, you can never make the mistake of adding a temperature to a volume, which is a nonsensical operation. But in C++, if you use just floats, you don't know. It's not going to warn you. Also, because of LLVM, Rust can compile to almost anything. It can compile to mobile, chips, it can compile to WebAssembly, but I'll show that in a bit. So with Rust, finally we have performance. Again, or I have performance, because I was trying to build something that needed performance. So these slides, as I showed you a little bit, are essentially an app written in our framework. It's a Makepad app, and I showed you that I did a little bit of live coding. But how does that work, right? Rust is a compiled language. You can't just change code in it. You have to recompile the whole application. So, step back a little bit. So, what are my goals with this? What is the goal? What are the goals of Makepad as a technology? So, first of all, I want to make Rust programming fun, right? So, why are you building developer tools? Why are you building these things? Well, to have fun with computers is a good start. You can always grow from there to make money with computers or make products with computers, but starting with having fun with computers is where it all started, with the Commodore 64, with the home computer. People wanted to play with computers. So that's a very, very fundamental piece in Makepad. Another piece is that I want the visual design tool back. I want the combination of code and visual design to live in the same space again, just like we had with Visual Basic. And in order to do that, to make it fun, to do new things, I need all the media APIs, I need webcams, I need audio, and I need live coding. So how do we do live coding with Rust? Well, I cheated a little bit. I made an extra new language, which is our UI language. It's a DSL, a domain-specific language, designed for styling and UI. And so from here on out, I'm going to show Makepad Studio. You can clone it from GitHub, and you can also try it on your own computer like this. You can run it, and everything you see here is in the repo. You can do anything I show you here on your own computer as well. So I quickly want to talk about so what is the makeup of Makepad app? How is it structured? So the framework is built in a layered fashion. We have a platform layer that talks to the operating system, that talks to the GPU, contains a shader compiler. So the programs that you write in Makepad are backend agnostic. So they run on WebGL, Metal, DirectX, and OpenGL. And that means that we translate the GPU programs that we use to style the UI. I'll show you that in a bit. And we have a UI DSL, the UI structure. And it's a little bit like HTML. I'll show it in a bit. And it contains the shaders, the shader programs that you run to style the UI. And then finally, we have the Rust code. And in the Rust code, you do your application logic. So let's look at a Makepad app. I hope the fonts are really tiny, I think, on this screen, but I can make it bigger in a second. Let's see. Let's start with the simple application. Simple. So here is a very simple Makepad application. It's a button with a counter, and so that contains the UI components, the events, and a Makepad application in source. This is a Rust file. This is the application file. Contains at the top in our current structure. You can also split it off in a separate file, but at the top it contains the language for the UI structure. So you should completely see this as HTML. You know, just think HTML, but without the shitty part. Because it's much simpler and much more controllable, and it always runs the same way everywhere. So it has a module system. You import the base and you import the theme, which contains the styled components. Then you define a window. And window is, it's just the root context of a device, of a window of an application, or in a browser. And then you can say here is a little function that I'm going to return a color here. Right, so this is the live coding. I can change the program code that runs on the GPU to create the background of this application live. This is very similar to ShaderToy. I don't know if any of you know ShaderToy. It's an online platform where people can play with GPU programs, and they make the most crazy artwork there. But this is the same, except, yeah, you can do also simple things with this, and for simple things, it only ends up being this function. So imagine that this function gets called for every pixel in the button, or in the background in this case. For every pixel in the background, this function gets called, and it blends two colors, in this case, two colors of gray. I'll make the bottom one red, then you can see. Now it blends from gray to red, and it uses as the index the Y position, which goes from 0 to 1. So yeah, this is a very fundamental primitive of styling. And then we have the body of the window, the widgets that are in there. The view item you should see as our div. It's a div, it's a node in the tree that contains child nodes. And here we have a button, a text input, and a label. These are widgets from our widget kit. We're currently working on making all sorts of mobile widgets as well. Hold on. So yeah, we have a desktop widget kit, as you can see. This is in the IDE, and we're working on other widget kits for mobile and web. And then when we go down in the application, you see the main struct for your application. In Rust, everything is built out of structs, or structs and enums effectively. And a struct is just a collection of values. But unlike JavaScript, for instance, these values are static in memory. They're essentially, they have a fixed layout, and just like in C++. And that is the big difference between a language like Rust and JavaScript, is that when you look up a value by referencing it or by accessing it, it doesn't have to compute at runtime where it's from. It knows statically in memory where it is. And that's the big difference between a language like Rust and JavaScript, or a big difference that makes Rust so much faster. Yeah, so we have the app, and then you use an event handle function. This is in Rust, because it doesn't have a garbage collector. You have to imagine that if you have an on-click handler or on-click closure, it cannot reference data easily outside. It cannot close over variables easily. If you know the history a bit of closures, and then you realize that closures and garbage collectors evolved together as a solution to being able to access data in the outer scope. But in Rust, similarly to C++, that is impossible, or in any case, it is very inconvenient. So the architecture that we've chosen with Makepad is to use essentially a polling architecture. And that means that for every event that comes in the signal into the system, like a mouse event or a draw event, this is the only function that gets called. So for every event, this function gets called, top down. And here we handle the draw event to draw the UI itself. In this case, we just tell the UI component to draw itself. And here we handle a click action on the button. So the way that works is you query the UI for the button and then ask the button if it was clicked. It's very simple, but it's a reversal of the model where you put an on-click event handler on a button. In this case, you keep asking all your components, hey, did something happen that we need to know about? So yeah, that's the basic structure of a Makepad application. It is different from what we know from other languages, but it's also extremely performant. Let's see. Yeah, and one of the main things that everybody always needs is what React is very famous for, is lists of template items. And we have a different way of doing that, and that I think is extremely fast and also quite ergonomic. Here we have a newsfeed application, just as a test of a scroll widget. Yeah, all this data that is in this widget is, in a real application, will be streamed from a server. and would be virtual viewport. Like not all of the visual items in this list will be generated in the render engine. You use a window, and this in Makepad this is called a portal list. And let me open it. So this is where you would write. Oh, that's not a one-handed operation. I should use another hotkey for zooming my text. So in this case, the draw loop, because this is all a single entry point for this function, and it's being called for drawing, then what you do is instead of tell the widget to draw all, you tell it like, hey, is there any widget in your draw flow that needs a custom bit of behavior? Then return from this function, and now you can draw it like a canvas API. This is called immediate mode. Immediate mode rendering is a form of very simplified way of drawing widgets. So instead of generating HTML, for instance, to generate a UI, what you do is you, at the moment that the widget needs to be drawn, you draw them manually like a canvas API. So for I in items, you draw all the items. You don't have to generate a UI structure that is then later on processed and processed and processed until you have the output. You draw directly, conceptually, because you can never draw directly. The GPU is doing all that stuff, but conceptually you draw directly. So here, this news list goes over the, hold on. Yeah, this is, when you see this, this is just a thing we need to be able to run the applications on a texture. So this application is actually running inside the IDE, but it's still a sub-process. So we made a little bit of a browser engine trick there, but just ignore that. So yeah, you loop over the items, and the list asks for the items by ID that it needs to draw. And then you can fetch an item, pick a template for that item, then you can parameterize the content, and then you draw it. And there is no other place in the application that I need to create, maintain, or do anything with these components, right? So it is similar to eGUI in that sense, if anybody has seen that. That's another UI kit for Rust. Makepad is hybrid immediate mode. So we have both a retain mode structure and an immediate mode structure. Retain mode structure means that there is a structure in memory that contains the UI, and immediate mode means that only at the point where you decide what to draw do you have a reference to the objects. Let's go back to the slides. Oh, did I close the slides? Here we go. So, yeah, we went through the logic of a Makepad application. So what is the biggest thing that we solved, right? What is the largest amount of code in a Makepad application? And that is the platform abstraction. That is how we can run on a lot of platforms. And I wanted to show you a little bit of the platforms that we can run on. So first of all, I've shown you the in IDE application, right? So we have the application in IDE like this. Oh, did I break it? I broke it. Okay, so we have the application in the IDE like this. We have the application outside of the IDE, right? Now it's a desktop application. We can also run the application in, let's see if I can do that. Simulator, open simulator. I'm booting a virtual iPhone right now. Okay, let's click iOS simulator. So now it's compiling. By the way, this is all clean build. So yeah, I think that is pretty quick for a complete clean build of an iOS application. It's only a couple of seconds. So now we have it running here in the iOS simulator. We can run it in WebAssembly, so I'm gonna just compile it. Oh, here we go. Compile WebAssembly. Oh, okay, that takes a little bit longer because I have to compile the standard library. If you compile for WebAssembly and you use threading, Rust, it uses Rust Nightly, which is a testing version of Rust, and it has to compile a custom version of the standard library. So it takes a little bit longer. But here's the same application now running in a web browser using WebAssembly. And now I want to show you it running on an actual device. Let me see if I can do that with one hand. I'll do it like this. And because you don't have a camera, I have written a little example application that opens a webcam. So there we go. And now I should be able to click Android. So now it's building the Android application. Let's see if it boots or if I broke it. It's building the APK, compiling the APK. There we go. Now this is a complete clean Android build and deploy happening from Rust and from Makepad. So most of what we've done is enable that workflow, right? If you look at the source code that we have, a lot of it is the platform layer, the GPU abstraction, so that we can run on all these platforms. And because it's live codable, that should work. Let's see if I can actually change the font size, for instance. Where's my font size? I think it's here. All right, so here we have it in WebAssembly, iOS, and here. Let's see if I can put it all on one screen. Right, I now change the font size, and it live updates on all the platforms. It also updates on the phone, but I don't have it on the network right now. So if you have your device on your local Wi-Fi or your local network, you will be able to live code directly onto the device. So this was the DSL, right? This was our little hack that we could use to live code on the device. But what happens if you're iterating on the code, right? How easy is that? Because if you write Rust, you always have to run cargo run after you change the code. Well, with Makepad, I've tried to. So if you click this button, it shows this little log test. And if I type 1, 2, 3, you can see it grays out a little bit for about 1.5 seconds. And then it comes back on, and that means it's recompiled. So this is how fast you can recompile with Rust. Oh, actually, I'm recompiling not just that application, but also my phone. Here, this is what happens if I change that. 1, 2, 3. There we go. Because all the builds are turned on in parallel, actually all the platforms that I just shown actually were recompiling in one cycle as well. So I think it's even going faster if I turn some of these off. So yeah, that's the multi-platform reach that you can have with Rust once you have a stack like this. Okay, let's see. Oh, so yeah, that's one problem of running your slides inside your IDE whilst you're turning things on and off. You keep turning off your slides. It's a little note to self. So all these platforms, it's great. This is the first time that I can write an application that is both high performance and multi-platform, right? I don't have to use web technologies to do this anymore. You can do this now with Rust. Yeah, so here I want to show you a few of the fun applications that I've built. For instance, one of the things is a Stable Diffusion UI. I'll show you. Stable Diffusion is an AI model that does image generation, and I found the existing web UIs for it rather lacking and limiting, and just not very fun. So this is essentially an image viewer but it is a very, very fast one. It is running on 10 cores, decoding PNGs. It doesn't even bother to make thumbnails. It just runs fast enough to not do that. This is actually a hybrid kitten axolotl. And yeah, we tried to make all sorts of weird combinations of creatures. This is a disco fly, or we tried to make fractal flowers. Let's see, what other kind of fun creatures do we have? I think we have, let's see, oh yeah, this is some kind of Kirby robot, eyes. And this was an interesting one. This was an attempt to make a bunny octopus. A bunny octopus. This is what AI spit out if you actually ask it to create weird hybrid creatures. It is surprisingly creative, right? A bunny octopus. It's just, yeah, it was mind-blowing. But yeah, now with Makepad, I could build this application in a matter of days and not a matter of weeks or whatever. And it runs everywhere. I can run it on my Windows boxes. I can run it on Mac OS. And it is so nice and fast, running 120 Hertz easy. So that's a nice example. Oh yeah, it also had a little extra window that you can put on your TV, so you can play with the AI with your friends as well. Let's see. We made a synthesizer. This is one of our examples. All of these examples are in the repository. You can play with it as well. Let's run the synthesizer. I think I should have audio as well. I'll run it standalone, so it's a bit bigger on screen. Release. Here we go. Synthesizer. So this is a synthesizer made by a friend of mine called This Is Not Rocket Science. It's Ironfish. It is actually a full-featured, fun synthesizer with all sorts of features, like let's see. And what is also fun is that now that you actually have these low-level audio APIs, this is not different from Logic Audio. I'm using the same APIs. So now you can also deploy that to web, which is something that has mystified me for a very long time. Oh wait, I did say I compile everything on stage, right? So I forgot to build the WebAssembly build. Let's see. There we go. And this runs even on mobile. I mean, the UX is not that great for this UI. We were also working on a mobile UI, but it being just an example, we don't have infinite time for it. But yeah, the same low-level audio APIs as we have on desktop is running now multi-threaded in WebAssembly. Similarly, we have a demo of using SEM SIMD and multi-threading. This is a fractal zoomer. Fractals were the first thing I saw when I was like 10 years old. I saw an MSX computer or something very, very old drawing a Mandelbrot fractal. And it has since then mystified me throughout my life how amazing that thing is, and also how fast computers are. So for the longest time, every time I got a new computer, I would run a Mandelbrot fractal zoomer on it to see how fast it was. So I think it was, yeah, that was my way of trying out my new compute power for at least 2000 to 2010. But since then, I think people got bored with it, and nobody updated the fractal zoomer anymore, the software. And I was like, okay, so maybe it's time to make a new example that that does use all the compute. So what you see here is essentially an image generator where the image is computed by the CPU. So it's essentially a Google Maps renderer, but it's using the CPU to compute the tiles. So here we have fractal zoomer. Let me change the colors a little bit because I don't like it. This is where the live programming is very, very nice. You can just open the fractal zoom. And so here you see the pixel shader, the little program that I use to style the colors on the screen, right? So here we have the colors. And the colors are produced by this function. This is a palette function. I think maybe this one's a bit nicer. And I think we can move it in a different direction maybe, outwards, maybe a bit slower. So yeah, you can live code the shader programs that are associated with it. The GPU in this case is not running the computation for the fractal. And the reason is GPUs, almost all GPUs only have F32, 32-bit floats. And if you're computing a fractal and you want to have a fractal like the Mandelbrot and you want to have enough zoom capability, you have to imagine that as you zoom into the fractal, your floating point number gets bigger and bigger and bigger and bigger in terms of the representation needed. And at some point you run out of bits and then it cannot zoom in any further. Thus, if you have an F64, which is what the CPUs have available, you can zoom in a lot further into the fractal than if you run it on the GPU. So this is why this is a hybrid renderer. It colorizes the fractal on the GPU and it computes it on the CPU. And it's a very nice example of how to write multi-threaded code in Rust, and also why Rust is actually great for multi-threading. We haven't talked about that yet, but Rust has something called fearless concurrency, and fearless concurrency allows you to write multi-threaded code without having to worry about race conditions or data races or this entire legion of possible bugs that you get in C++. C++ multi-threading is like juggling chainsaws, and this is like, you know, playing with a bunny or something cute. It's very, you can do this when you're tired and you just want to have a quick multi-threading thing. In Rust, you can safely write multi-threading code when you're tired, which is an unbelievable achievement for a language in my book. So yeah, if you want to learn about writing SEMD, so SIMD code, SIMD code is a single instruction, multiple data. So for every loop, I compute 4 values of the fractal. This is something that's also available in Rust. It's called portable SIMD. This is also, I think, a unique feature so that you can write that single instruction, multiple data instructions for multiple platforms in one way. And that's, yeah, I don't think I've seen that before either. So yeah, computation. My computer is now, I can do stuff with the compute again. I can use the GPU, I can use all my cores, and that means you can do more, have more fun with your computer again. Let's see, let's go back to my slides. Sorry for it being so small, slides. So yeah, the model that we're choosing with Makepad Studio is that builds are switched on or off. So you don't run a build is active, and that means that it automatically rebuilds when it needs to, it hot loads when it needs to, and you can just turn them on and off. So when you're working on a project, you just turn the build on and you never look at it again whilst you live manipulate it. So that's a change I hope we can bring to the Rust space. So yeah, fast compute is needed, right? If you want to build an application like a code editor with things like animated code folding, right? I don't remember if I've shown that in the current example. But my code editor here can do animated folding. And this is, I think I mentioned that in the beginning, that I couldn't do this with CSS and HTML. And now with Rust, again, we have the performance to do these kinds of interesting things with an editor that we couldn't do before. So performance is needed. I think we've grown accustomed to not using performance, but that is different to not needing performance. Like with a web UI and a web form, choosing to not use animations or effects or smooth interface capabilities because web makes it so hard, I think is not the best way to go. It is much nicer if we can actually do it again. Similarly, if you do if you're trying to build an IDE for an IDE, right? As I said as well, like the only way I can judge if a tool is any good is if I can use it myself. So the question is, can I use it myself? Well, let's see. Well, I guess the IDE boots up in the IDE. So that's at least step one of the problem is done. It looks like I can use it myself. But once you're doing the IDE with the IDE, what if you want to debug the IDE debugging the IDE, right? Well, let's see if it does two levels. Well, there we go. We can continue to develop the IDE as we try to develop the IDE. And well, this last level, I have to be honest, this is just for show. I've never needed this one. I have no idea also why you would want to do this, but you can. So, yep, there we go. Let's, so yeah, I think I can use it myself, and that is the first time in a decade that I'm here, and this is thanks to Rust. You know, these are child processes. They cannot take out the IDE like a browser. Like so, the browser IDE I had was super unstable because when the browser goes down, the whole development environment goes down with it. And because in Rust you can just write true desktop applications with process isolation, cross-process sub-processes, yeah, you can actually solve your problem again. So I'm very happy with that. Let's see where I am. Let's go to my slides. Now inside the IDE, I think I've arrived at the end of my presentation. It's a little shorter than a full hour, but these are the links to Makepad. This is the Makepad website and our GitHub. On our GitHub, you will find the link to our Discord, and my Twitter, all the other people involved as well. So if you want to engage us, you want to play with the software, it's all there. Everything you've seen here today is on GitHub. Yeah, if you want to continue the conversation, Discord is a great way. So yeah, hereby, are there any questions? Then feel free to ask them.
有没有人有任何问题？
This is Kage. So very impressive work, and I have a huge respect for Cloud9, which we actually used to develop our own IDE for a project in 2016. So I'd like to ask one question. You mentioned visual programming in your as one of your goals, and yeah. I'm curious. What kind of visual programming do you support in Makepad right now? Because
so yeah, I didn't show that yet because it's not done. This is really new. Like the fact that I could do all of this is probably a week old or something like that. So what we've done is hold on. So this application is pretty much our test of. This application should be designable in our Figma-like visual designer, right? So this application if you look at the UI structure for it, here's the UI structure for the synthesizer. We designed it so that the code that you see here is essentially machine editable as a Figma-like document. So if the visual designer that we're working on right now will show this application sort of splattered out in all the components that it has, just like a Figma design for an application. So that is the next feature that we're going to add over the next couple of months. That's not visual programming, but that is visual design for programming, right? This is our UI design tool. So yeah, we don't have that yet. I couldn't show that. As for visual programming, I want to have a flow graph widget at least, so that people can build all sorts of visual design, visual programming tools with it. For Makepad itself, I'm undecided how to use a flow graph, if it's beneficial or if we should focus more on the code side, because the problem with pure visual programming is that it gets messy really quickly. You can do simple things quickly, but the moment you start to need more logic, yeah, I'm kind of on the side that we should make the programming side as easy as possible instead of going to a flow graph. But we might actually add a flow graph as well, because I see also Unreal blueprints and I see the value of a flow graph sitting in between code and a design. But yeah, undecided.
So if there are questions, can I ask a second more technical problem? I see in most of the examples, you're basically assigning all the attributes to the objects. So I'm curious, for example, do you support also some CSS like styling?
Yeah, we do. Yeah, that example was indeed not the prettiest. Let me see. I have an example of that. Where did I put it? I think it's in the IDE itself. Hold on. I think I put it in the IDE itself. So the IDE has a log viewer. So every component in the IDE is also a component in the application. So the log viewer here, which is kind of a cool little thing. Let me show you. So we have newsfeed. Let's run newsfeed. And then app. And let's see, yeah, let's just make let's make a big loop. Right, so I don't know if you can see it, but I think I'm logging in the order of 1 million lines of log to a second to this little widget here. It still remains fully usable. And the way I do this is I have a virtual, just like this, it's essentially the same widget as this list, except you can log 1 million lines of log a second to it. And it looks like this. See, where's my log viewer, log list? I'll make the font bigger, of course. So here you'll see something that looks a bit more like JSX. Right, so here we have a log item with a location. And instead of setting the values on the widget directly, you can write it out like JSX or like a structural overlay over the UI component. So you spawn the UI component, and then you can override values just like you would apply a piece of JSX. Is that what you asked? Yeah. Yeah, okay. Any other questions? All right. Well, thank you very much, and yeah, hope to see you on Discord or have fun with playing with the software. Thank you.
Thank you, Rick.